Okay, next, we're going to talk about effect sizes. We've spent a lot of time focused on statistical significance, looking at and interpreting the unstandardized effects, the B weights within our GLM analyses. So it's also important to think about how large of an effect you have. Not enough to just say this is how related it is, but it's also important to think about that within context. So we're going to talk about effect sizes. So an effect size is just another way of describing the magnitude of any sort of effect. What an effect size is another way to describe a result. And what an effect size is not is a p-value. P-values are not effect sizes. P-values and effect sizes are not related. Now, the advantages of standardized effect sizes is that it allows you to easily and quickly compare between studies, between samples, between contexts, and you can compare even when studies are using different measures of the same construct. So you have one that uses one survey to assess affect, and one that uses another. Just because the questions are different, the total number of questions may be different, but the constructs should be similar. Now, most commonly, you'll see effect sizes talked about in terms of group differences. So when we're examining treatment effects from something like a causal research design that we were just talking about, it's a standardized difference between two means. So when you're thinking about a standardized difference between two means, the most common one that you'll see is called Cohen's d effect size. And Cohen's d is a really nice effect size because it's pretty flexible. It can be calculated in many different ways, but it's all different variations on this same idea, which is Cohen's d is the mean of one group minus the mean of the other group over some sort of standard deviation. And don't worry, I'll explain this a little bit more. The idea behind Cohen's d is that you're expressing the amount of difference that you observe between two groups. And it's expressed in standard deviation units. When I say pooled standard deviation here in this equation, it means the standard deviation of the entire sample. So if I want to say, look at the difference between people who are in the morning class or people who are in the afternoon class, I would take the mean from the morning class and the mean from the afternoon class, and I would divide it by the standard deviation of everyone. That's the pooled standard deviation. When you have a treatment group and a control group and you want to compare the differences between the treatment group and the control group, oftentimes that's estimated like this, where you have the mean of the treatment group and you subtract the mean of the control group, and then you're dividing by the standard deviation of the control group. And we do that because the standard deviation of the control group is what we think would be more representative of what would have happened if you hadn't gone in and messed with people in the treatment. So the standard deviation of the control group is more representative of people as they just are. Whereas the standard deviation in your treatment group could potentially be either smaller or larger than you might find ordinarily. And you interpret this as the standardized mean difference between the treatment group and the control group. You can also use Cohen's d to talk about the difference between two measurement occasions. So maybe the beginning of the school year and the end of the school year. So you could do this by measuring the mean at time 2 and subtract the mean at time 1, and you divide that by the standard deviation at time 1. Or you can divide it by the standard deviation of everything if you want to, but the standard deviation at time 1 I think is more traditional. We use the standard deviation at time point 1 because it represents where they were when they started. And the interpretation of this is the standardized mean difference between the two measurement occasions. So it's a nice way to talk about how much change occurred in standard deviations from the original time point. So you've seen that I just gave you 3 different ways to calculate Cohen's d, one right after the other. It can be calculated in different ways, and all of them are called Cohen's d. So it's important when you are talking about Cohen's d effect sizes that you explain how you calculated it when you are publishing on it. So if you're reporting a Cohen's d, you need to also report what you use to represent the mean and what you use to represent the standard deviations. Cohen's d has an unlimited range. It can be infinitely big and infinitely small. Negative infinity to positive infinity. But you will often see these things that they call Cohen's benchmarks. They're commonly used to describe effects. And I think if you read the readings that you had for this week, you will see people pushing back on this idea of these 3 benchmarked effect sizes. But I'm going to tell you what they are because you'll see them come up in papers a lot. They'll argue that small is 0.2, medium is 0.5, and large is 0.8. But again, look at the readings that you had for this week because those benchmarks are basically meaningless. What is 0.2 standard deviations? Is that big? Is that small? It's better to contextualize these findings in other ways, and that's what the 2 papers, the Kraft paper and the Hill paper, were about. I'll show you the Hill paper right now. So from the Hill paper in 2008, they walked through and looked at the typical or average annual gain in effect sizes based on nationally normed tests. And they did this for reading and they did it for math. So they did this as time 2 minus time 1 divided by the standard deviation of time 1, essentially. And they have about a 1.5 standard deviation increase from kindergarten to 1st grade in reading. And about a 1.14 standard deviation increase from kindergarten to 1st grade if you're looking at math. So this is really useful because if you're trying to describe how big of an effect you see, and you're studying kids who are in, say, 1st grade, you can talk about it in terms of months of schooling. You can talk about it in terms of how much they typically would gain during the school year. So these sorts of benchmarks are really useful for you to be able to contextualize what it is that you're finding. Instead of just saying, Cohen says 0.2, you can use these if you're doing reading and math. They also took this another step further. So just to show you another example of how you can use these effect sizes, they also did performance gaps. So they did between black students and white students at 3 different grade levels. So in reading at grade 4, there is a gap between black students and white students that's equal to about 0.83 standard deviations. So if you are trying to examine a gap between how well students are performing in your particular assessment, you can use these as benchmarks to compare them to. Okay. Now, the next thing I want to do before we move on to correlational measures is I want to show you, this. Where did he go? Well, sorry everyone, I thought this was going to be much faster than this. There he is, our psychologist. I had his name wrong. Let me share the screen and I'll show you all what I'm looking at. here we have an interactive visualization. Oh. An interactive visualization. And so I'm going to zoom out a little bit so you can see. So here is a cool illustration of how large of a difference we're looking at when we're talking about the difference between a control and treatment group. So here we just said Cohen's benchmarks are D of 0.2 as being small. So these are two samples, and look at how close they are together and how much they overlap with an effect size of 0.2 standard deviations. And there's 0.5 standard deviations. 0.2 is pretty moderately, I mean, they call it small, but it is an effect that we would look for within education. If you have an effect size of 0.5, we jump up and down and are very excited about it. It doesn't happen that often. 1.0, you end up with quite a big difference. I would say definitely there's a difference here between these two groups, no question. So I'll put the link to this in the I keep wanting to say show notes. In the on Carmen, thank you, for today, so that you can play with this yourself and see just how big these effect sizes really are. Anybody have questions about that particular visualization or about what effect sizes between a treatment and control group mean? No? What about 2 standard deviations? Oh yeah, that's a dream. If only. Look at that tiny effect size, 0.01. No difference at all. Okay. Start share. For some reason, it's trying to share the wrong screen. Okay, so, but effect sizes are not just for differences between groups. They're also available in correlational models. So when you're in a correlational model, it's not a difference between groups, but it's a way to measure how strong of an association you have. You can still use effect size type measurements for correlational models. And here are a couple of options. The first one is a correlation. A correlation in itself is a standardized effect size, and it's typically benchmarked the same way as Cohen's D, 0.2, 0.5, and 0.8, as small, medium, and large. But once again, are those valid? Yeah, maybe we need better benchmarks than that. R squared, which you're familiar with from all the GLM modeling you've done, is the how much variance in the outcome is explained by your predictor or predictors. That is also an effect size. It is agnostic to the particular units that your assessments may be in. A beta weight is the standardized version of the B weight. You've been interpreting the B weight all along. The B weight you're interpreting as 1 unit change and how much your corresponding increase in Y. With a beta weight, it's the same idea, but it's within standard deviation units. So you're still saying it's how much it increases, but this time we're in standard deviation units, so you can compare across multiple different measures and studies. The last one I'll tell you about is one that SPSS will spit out for you. It's called the eta squared. The eta squared is about the sums of squared errors. So remember, we're always in model comparisons mode, so it's how much of the error you've decreased in your model. So we're looking at the sums of squared errors for the effect out of the total of the sums of squared errors in your model. And they typically benchmark it like this. There's so many more effect sizes, and I want to show you this little link right here that you can follow. And if you click it, you will see this. And what they've done is they have scoured the research literature, and they've pulled all of these different kinds of effect sizes, and they've put them on a similar scale. So if you have an eta squared of 0.01, they consider that to be small. An eta squared of 0.06 is medium. So here's all these different ones, which my goal here is to give you this tool so that you can use it when you're evaluating research studies, or when you need to write up your own research studies, you can look at this particular tool and find a way to talk about the size of your effects. The other thing I wanted to show you is this little guy. This is the effect size calculator, and this was made by James Wanhoro, who just graduated from our ESQREM program. And he wrote this when he was a TA for one of these classes. And this is if you have different types of effect sizes you want to calculate for different types of tests. He has them sampled out right here, and you can hop on here and you can use these to calculate effects. There's a partial eta squared. There's an r squared. No, I don't think we won't learn the HLM stuff in this class. So, both useful tools that I thought you might like to know exist. Okay, so what I'm hoping is that you all will be able to use effect sizes in your actual research as you're writing up and talking about your results, that you're able to take and calculate some of these.